nanohub.org.
Online simulation and more for nanotechnology.
Now, this is the last topic on Bayesian inference, which is basically the backbone for solving model calibration problems. And after that, we're gonna do one lecture on optimization of very expensive functions, which could either be simulations or experiments. But this particular lecture, both these two last lectures are basically touching the state of the art in the field. So in particular, variational inference is the state of the art in Bayesian inference. And the particular method that I'm going to talk about, automatic differentiation variational inference, is the most powerful approach to automate Bayesian inference. It's not trivial to understand it. It's probably impossible to understand it in 1 hour, but we'll give it a try. We'll try to simplify, to at least give you the idea of what it does. But the whole point of this thing is to completely automate Bayesian inference so that you don't have to think about it. Okay? That's the whole point. So, and I think eventually in like perhaps 10 years, you're going to be able to solve engineering problems, calibrate models, infer parameters on models, etc., without really worrying too much about what is done on the background. But nevertheless, we're going to look inside it today. All right, so this is our objectives for today. We're going to use variational inference to approximate the posterior of a Bayesian inference problem. Okay, pretty much what we have been doing with Markov chain Monte Carlo and sequential Monte Carlo. We're going to look into the details of automatic differentiation variational inference. We're going to open this black box and look inside it and try to grasp the main ideas behind it. And then if time permits, it's very unlikely, but if we have like 10 or 15 minutes left, you'll get the chance to play a little bit with it, with variational inference on the handout. We have a handout where variational inference is implemented, and you should check it out no matter what. All right, so what is our problem definition? We have a model, which is basically the definition of a likelihood. It includes at the same time some model that may depend on physics and the measurement process, a model of the measurement process, and it is like that. It defines basically the probability of x given theta. X is the data you are going to observe. Could be one variable, it could be several variables, it could be a time series, whatever it is. We're just going to call it x, okay? Because we're going to create a very generic methodology. And then theta are any parameters you may have, okay? So all of the problems we've done so far are of this form. You have probability of x given theta, but x may be time series, right? And theta may be 10 parameters. But they're all like that. And we always had a prior on the parameters, p theta, and this may factorize on the components of theta, whatever they are, but it is always some p of theta. And the model calibration problem, we said that we basically have to characterize the posterior, which is the probability of theta given x, given by Bayes' rule. You have likelihood times prior, and this guy right here is the normalization constant, which you can write it as px. And the normalization constant is basically given by this integral here. We just make sure that whatever we have here integrates to 1 when you integrate over theta. All right. So this is our problem. We're given, somebody gives us this, or we define this, the model. Okay, let's call it the model. But it is also the model, the physical model, and the model of the measurement process. We have a prior, which is our state of knowledge before we see any data, and x is the data we see, and we want to characterize this quantity right here. That's our problem, okay? Let me remind you that we did MCMC right? We did MCMC, even though we didn't know that, we're able to take samples. That's what you're doing in your homework. And then we said that this is a very useful quantity for doing model selection. If you had two different models, you could use this quantity to compare the two models to each other. But you cannot compute it with MCMC, and we introduced sequential Monte Carlo to compute this quantity. All right? Now, variation inference is going to basically characterize this distribution and give us an estimate of this in a completely different way, without really sampling. It will pose and solve an optimization problem. You will see how it's going to be done. So I'm saying here, how did we do things up to 10 years ago? But it's really, even now we do things like that, especially the engineers. Here's how we do science, let's say. So we create a model, and then we come up with a specialized methodology to train the model to find its parameters. I mean, that's what you do if you want to be Bayesian, right? If you just want to do a parameter sweep, if you have 2 or 3 parameters, you just do a parameter sweep. That's what engineers do. Then you come up with a specialized methodology in the sense that you derive a Markov chain Monte Carlo specialized for your problem, or a sequential Monte Carlo specialized for your problem, right? Or a maximum likelihood maximizer specialized for your problem. And then you implement this methodology in a computer language like C, Python, MATLAB, whatever you want. Then you verify that your methodology works. How do you do that? You find a problem with a known solution and you make sure that it at least can solve this problem. Then you solve your actual problem. Should be, let me take the actual data and plug it into my methodology and see what I get for my parameters. Then you look at your results, you analyze them, and you say, if they're good, okay, I'm done. Good is very debatable, okay, but you say you have a way of doing that. If you're not satisfied with your model, you go back and you change it a little bit. You say, oh, maybe I do not capture this effect. Let me add it in my model. Let me make it a little bit more complicated. Let me change this to that. And then you have to go all over again and do the whole process again. You have to you have to go and change your algorithm. You have to re-implement it. You have to re-verify it and go over and over again like that. Okay, this is how things were done up until very recently. But with the advent of tools like PyMC, right, we were able to automate this process here. So PyMC belongs to the category of probabilistic programming packages, okay, which means that they're packages or computer languages, if you like, in which you can describe a model with simple commands. For example, you say, well, x is a normal random variable, and then I have an f of x that is, I don't know, I have to solve a finite element, to evaluate a finite element solver to get f of x. So I get f of x, and then what I observe is y, which is normally distributed with f of x as the mean, and then another variance. So all these things, right, you can describe it in languages like PyMC, and there are other probabilistic programming packages that I will refer to later. And then PyMC creates for you a Markov chain Monte Carlo sampler that is already validated because we know that it works, okay? And then you just sample from it and you just analyze your results, okay? It's not yet fully automated, as you may discover while doing your homework, in the sense that it doesn't just work. You have to know what goes on behind the scenes to really make it work. But the whole point is to automate these things so that, you know, as a practitioner, you just worry about your model, okay? You just do science and then you just let the CS people worry about, you know, all the stuff that are inside here, and then you just analyze your results, okay? We're not there yet. I'm saying, how do we do things now? But right now, this is kind of like, it's not a black box. You can you still need to see inside to understand what's going on. And I don't think that you can write a paper where you say, I just use the black box and that's how I found the parameters. Especially if you find something that is highly non-trivial. Anyway, so probabilistic programming is what we did with PyMC and PySMC, trying to automate this. And it worked like that. We programmed the joint distribution. So if you pay close attention, this is what you define in PyMC. You say you define your random variables, and then given some random variables, you define what you observe, the probability of what you observe, right? That's basically what you did. So this is the joint distribution of the observed data and all the other parameters that you have in your model. And it's always like that. You can always just think of it like this, okay? It may be more complicated in the sense that this may factorize in a more detailed manner, but it's always this guy that you are programming, the joint distribution of the variables. So as soon as you tell PyMC or PySMC what is the joint distribution of your random variables, then it can just operate automatically. So here's some other packages that do probabilistic programming, and some of them have more advanced features. Especially these three have more advanced features that PyMC2. PyMC2 is what we have been using. There's a good reason for that, which I will tell you in a while. Now, BAGS is actually the first probabilistic programming package. Now, BAGS stands from Bayesian something, okay? I don't remember what. And it started as a Windows package. It's basically a Windows program. You just import a text file where you describe your model in a simple programming language, and then you just hit run and it starts doing MCMC. There is OpenBAGS, which is a free version of WinBAGS and open source version of WinBAGS, but it's not that well maintained at this point. It doesn't contain the state of the art. PyMC3 is the successor of PyMC27, and the main difference is that PyMC3 is written in a package called Theano that uses symbolic calculations to get derivatives of whatever you give it, okay? So the problem with the classic PyMC is that it used simple Python code, so it couldn't take derivatives of your functions on its own, okay? In PyMC3, basically what you define is the computational graph of your model, okay, but it's hidden from you completely. You don't even realize that you're doing that. The syntax is very similar to PyMC2, but because it uses this computational graph, it can take derivatives. And by taking derivatives, you can do things like Hamiltonian, Monte Carlo, or variational inference, which is what we're going to talk about today. Now, the reason I introduced first PyMC2 and didn't go directly with PyMC3 is because PyMC3, in PyMC3, you have to implement every single thing using each language. So you cannot just, you cannot say, oh, I have a finite element model, which is basically a Python script that calls ANSYS and then processes the result. You cannot do that with PyMC3 or any of the other packages. You can only do it with PyMC2. PyMC3, you have to, I mean, you can create a surrogate of your finite element model and plug it in there, but you cannot directly call something that is outside of the capabilities of PyMC3. So that's a very big restriction. I mean, it is possible, but it will probably take you 6 months to do it. It is possible. You're going to have to learn what's inside it to do it. Anyway, Stan, I haven't really used it, but it is very popular in CS and economics field. And it is basically, it has interface in many different languages. So you can create and run Stan models from Python, MATLAB, Julia, Java. So I'm not sure exactly what it does. Edward is a Python package that uses that pretty much does what PyMC3 does, but it uses TensorFlow, which is a Google package for symbolic calculations. So this uses Theano for symbolic calculations. This uses TensorFlow. So this is useful if you want to do Bayesian inference on deep neural networks, because deep neural networks are typically defined using TensorFlow. But anyway, you don't really need to know all these. Some of them will be dead in a while anyway. PyMC3 is probably your best bet forward. Or Stan. Edward is not very mature yet, is it? Can you install it without in like 5 minutes, or does it take like a day? Yes. Okay. Then you can also try Edward. Is there a stable version of Edward?
Is there what?
A stable version of Edward?
You need at least TensorFlow 1.2.
Yes, but Edward, is it like a full version number, or is it like a beta version?
No, it is a full version.
Okay. Then use anything you like, okay? But there is a learning curve for each one of them. They can pretty much do the same things, okay? But you're gonna have to put the time, at least 1 weekend for each one of them. All right, so why do we want to go beyond MCMC or sequential Monte Carlo? What is the problem? I mean, it seemed to work, right? Well, apart from the fact that, so I'll tell you one by one. So MCMC and sequential Monte Carlo, especially the ones, the versions you get by just pulling the crank on PyMC, they're going to be slow. And they may be too slow for the real world applications. And by real world applications, I mean when you have huge data sets, or when you have very high dimensional parameters to infer. And really high dimensional is relative. It could be 10 in your problem, or it could be 100 or 200, depending on what exactly the parameters are. And in general, to get efficient code for a real world application, it's not sufficient to just implement the model in PyMC or PyMC3 or Edwards or Stan, unless you're willing to wait forever, and then you're not going to be able to validate your results. So to get something efficient with MCMC and SMC, you need to go inside your models and design an MCMC sampler that is finely tuned to give you fast inference for your problem. Exploit the structure of your problem to get something fast. So if you want, I don't know, something that does online inference to be used, I don't know, coupled with a sensor that does something in a real-time manner, you can't do it with MCMC or sequential Monte Carlo. You're gonna have to open the black box, do something that is just right for your model. And of course, the starting point is always the posterior. Right? So the question is, how do I approximate the posterior fast? Okay? And you're gonna have to look at its structure to get something fast. So there is a little bit of, I mean, for every given problem, there's definitely something you can do, but you need to open the black box. All right. So automatic differentiation variational inference attempts to, I mean, variational inference is an old idea. Now, automatic variational inference started with these guys. This is a very new paper. This is 2017. Okay, and these are all guys from Columbia. David Blay is the leader of the group. He's one of the biggest names in machine learning right now. All the rest must be students.
Andrew Gelman is the guy who wrote the book on Bayesian inference.
Okay, yeah, I would say that Andrew Gelman is probably not a student. But everybody knows who does the work, okay? The students do the work. So, at least the coding. The professors got the money to fund the project. And this particular paper, if you look at the acknowledgements, has been funded by 5 different grants from spanning pretty much all the funding agencies, perhaps except NIH. But they have funds from NSF, DARPA, so everybody acknowledges that this is a very important contribution. And I'm happy to say that you should be in a position right now to understand what this paper is all about. All right, so my exposition from this point on is going to follow the paper very closely, but I'm changing the notation a little bit to match it with our own. But if you really want to look into the details, you should look at this paper and the references therein. Okay, because the paper is probably not enough. But you will get the basic idea. So I remind you that this is our problem. So we want to characterize this, the posterior distribution, in a fast way, and we want to come up with an algorithm that kind of does that automatically. Okay, so here's the idea of variational inference. Variational inference is a very, very old idea. It comes from statistical physics. So it's at least 100 years old. But it has been revived in machine learning and especially probabilistic inference in the past decade or so. And now with the advent of fast symbolic computations like Theano and TensorFlow, these guys were able to automate it. So here's the idea. We want to approximate the posterior, okay? And what we're going to do is we're going to pick a family of distributions within which we're going to approximate the posterior. So we say we don't really know what the posterior is. Okay, it could be any distribution, but let's parameterize it. Let's pick a specific class of distributions within which we're going to try to find that. Okay, this class of distributions is defined by Q. Q is to distinguish, to understand that Q is the approximation of the distribution, and these phi here are parameters that you use to describe this distribution. One example that you could use, trivial example, would be the Gaussian. Right? So you say, whatever my posterior is, I'm going to approximate it with a Gaussian distribution. And that phi there will describe the parameters of the Gaussian. Or it could be something else. Okay? In this case, we will end up using a Gaussian, but after a transformation, so this is not going to be exactly a Gaussian. Okay? It's going to be a transformation of a Gaussian. Anyway, so step number one, you pick a family of probability distributions within which you're going to approximate the posterior. So if you like, if this is the family, let me draw something like that. If this is the family of probability distributions, Q theta phi, characterized by phi, and this is the true distribution, P theta x, right? You're kind of trying to find the probability distribution that is closest to the true one, okay? I don't know, you can even define something like that if you want, okay? Like an orthogonal projection to the space of probability distribution. It's not exactly that what we're doing, but you can think of it like that. Like this is the space of all the distributions. Each point is one distribution. This is our distribution, the target one, which may be outside of that space, and we just want to find the closest one. Okay, does that make sense? How do we define closeness between two distributions? We define it by the information loss, which is a concept from information theory. It's basically, the information loss is called, we're going to talk about this quantity in a while, it's the Kullback-Leibler divergence between Q and P. And let's say, you can interpret it as the information loss you incur when you change the truth for the approximation. It's not exactly that, but you can interpret it like, you can think of it like that. Or you can think of it as a distance, in quotes, because it's not a distance, but you can think of it as a distance between the truth and the approximation. And you want to minimize this distance, right? So the idea of variational inference, this is basically the only take-home message that you really need to take home with you, is the following. You have your posterior, and you say, here's a huge family of distributions within which I'm going to approximate the posterior. How do I pick an element from this family? I pick the element that minimizes the information loss as I go from the truth to the approximation. How is the information loss captured? With the Kullback-Leibler divergence. Why? Big story. Okay? What is KL? What is the Kullback-Leibler divergence? The thing that we're trying to minimize to select the best distribution. So the Kullback-Leibler divergence is basically defined like that. And if you pay close attention, you will see here things like the entropy, right? So you see here, you clearly have with this term and that and this term right here, you have minus the entropy of Q. Right? So when you're minimizing the Kullback-Leibler divergence, you're maximizing the entropy of Q. So this is compatible with the maximum entropy principle. Well, you also have this term that combines Q with P, okay? Which is a measure of how close Q and P are. Another name, this is a quantity also used in physics, where it is known as relative entropy. Okay, relative entropy because it measures the entropy of Q from P in some sense. So if you remember when we talked about the maximum entropy, we said that the entropy of a continuous distribution was not really like that with a minus sign in front of it, but it needed this thing. You needed to measure it from another distribution. So we have already talked about the Kullback-Leibler divergence or the relative entropy in these lectures at the beginning. But anyway, if you want to learn more about that, you can start with a Wikipedia article, okay? But it will take a while to develop an intuition about why this quantity corresponds to the information loss that you incur when you swap the two distributions. Some properties of the KL. First of all, it is positive. Okay. You can prove that. It's not a big deal. You can show, and this is an important fact, that if it is 0, then the two distributions are the same. I mean, it would be a ridiculous thing to minimize if this wasn't true. Okay? I hope that makes sense. So if you manage to make it 0, if you make the information loss 0, the two distributions are the same. But it is not a metric in the mathematical sense because it is not symmetric. If you swap the two, you don't get the same result. Now, of course, if it is 0, if one of them is 0, the other one is going to be 0. Okay, but it's not the same thing. So the information loss going from this to that is not the same as the information loss going from that to that. It's a little bit different. But if you make them both 0, then you have a guarantee that the results match, the two distributions match. And that's why we don't call it the Kullback-Leibler metric, and we call it the Kullback-Leibler divergence. Okay? Alright. So minimizing the Kullback-Leibler divergence is equivalent to maximizing this quantity. Why is it equivalent to maximizing this quantity? It's very simple to see. I mean, I have space to do the proof in the next slide, but I will probably skip it. I can just tell you. You just expand this. Alright, you put a minus sign in front of it, and you will get this more or less. Not exactly this, you're gonna get something similar to that. Okay? You're gonna get, if you expand this, you're gonna get minus this plus a constant that doesn't depend on theta. That's what you're gonna get. Okay? And that constant happens to be the model evidence. and you can actually show, perhaps we'll just start the proof but not finish it. You can show that this quantity that you can maximize instead of minimizing the Kullback-Leibler divergence has an upper bound. So there is a maximum that you can get. You can really go beyond that. And that maximum is actually the evidence. And that's why this quantity is called the evidence lower bound, or elbow. Okay? Why would you do this instead of, why would you want to maximize this instead of minimize that? So you see, this is a minimization problem with a lower bound, 0. This is a maximization problem with an upper bound, the evidence. Okay, if you minimize that, and let's say you get a minimum Kullback-Leibler divergence of 0.2, it doesn't really mean anything, right? How much is 0.2 of Kullback-Leibler divergence? But if you maximize the elbow and you get, let's say, 100, this 100, it's definitely lower than your evidence. So your evidence is more than 100. So if you maximize the elbow for 2 different problems, you can compare the maxima you find and do model selection. Okay, that's why we work with the elbow. Okay, and I will just show you how the proof would go, right? So you would just expand it. So you would say integral q theta phi log q theta phi d theta minus q theta phi log p theta x d theta. This thing here is minus the entropy of Q, and then in this term right here, this term in particular, you know that P theta x is the joint distribution of x and theta divided by the evidence, right? So this you can write it as integral Q theta phi log px theta divided by px d theta, and you take it a step further, you have again minus the entropy, and then minus q theta phi log the joint d theta, and then you have plus, right? So you have plus the integral of q theta log px, but px does not depend on theta. So you can just integrate over theta and you're going to get 1, right? So here you're just going to get plus log px. Okay? And this thing is greater than or equal to 0 because the Kullback-Leibler divergence is greater than or equal to 0. So you can move these things to the right hand side, and that's your elbow. And it was instructed to do the proof because it just found a typo. This is log. Okay? It's log of that. Alright, but you see that there's really not a lot of math behind it. It's trivial. Alright, so instead of minimizing the Kullback-Leibler divergence, we're going to be maximizing the evidence lower bound, and the maximum we'll find will be an estimate of the evidence, if you like. Okay, so we can use it for model selection. Alright. So we have casted effectively the inference problem, the Bayesian inference problem. We changed it from a sampling problem to an optimization problem. All right, so you have to minimize a quantity. Now, to minimize that quantity, you typically have to do it so that the constraints of the parameters are satisfied. All right, so some parameters must be positive, some parameters must be within specific bounds, and now the parameters I'm talking about are basically the phis. right, in your parameterization of the posterior. So these phi's may have specific, actually, no, I'm not talking about the phi's, I'm sorry. I'm talking about the thetas, okay? So your thetas may be positive. They have to remain positive, or may be within specific bounds. So they have to remain within these specific bounds. So ideally what we want to do is we want to use a map that will remove these constraints from the parameters. For example, if the parameters are positive, take the logarithm to remove the positivity constraint on theta. If your parameter is between, 0 and 10, take a map that will put it into the real line, like the inverse of a sigmoid or something. So in general, you can always find, if you know something about theta, you can always find a map that will take the thetas and map them to the real space, to a Euclidean space. The support of theta right here is just the subset of the space on which the prior has positive probability, okay? So it basically corresponds to all the values that theta can take. This is what it is. Anyway, and we're gonna do that with the real parameters. So, what we're gonna get basically is another variable zeta, okay? So zeta is gonna be a transformed version of theta that is just real numbers. Why? Because it's just easier to deal with them. That's why. Now the posterior in terms of the new parameters, zeta, so if you ask what is the posterior of zeta, you can get it with a standard formula that tells you how to transform the probability density of random variables. It basically says that if you want the joint distribution of x and zeta is a transformation of theta, then it's going to be this, where this is the joint distribution of x and theta, with theta being the transformation, and here you have the Jacobian, the determinant of the Jacobian, of the inverse of the Jacobian, okay? This is what you have here. Why do you get that? This comes from transformation, change of variables inside integrals, okay? Anyway, but this is what we do before we start. So whatever variables we had, let's say that we had positive variables, we knew that the variable theta was positive. We didn't want to work with that variable because of the positivity constraint, making things a little bit weird. So we remove the positivity constraint, for example, using a logarithm, and then the new variable zeta, which is just the transformation of theta, will be unconstrained. And you see how the prior and the posterior change. Alright, now that we have managed to transform all the thetas so that they are unconstrained, let's talk about what kind of Q we would use, what kind of distribution we would use to approximate the posterior. So obviously the first step would be to use a Gaussian because it's the simplest one, okay? And one of the reasons we transformed the random variables was so that we could use the Gaussian. So the very first approximation scheme is called the mean field Gaussian variation approximation, where basically you approximate the posterior within this class. So you say that my posterior is going to be a normal, like a Gaussian, with a mu that is unknown and a diagonal covariance matrix. Okay, so you have one sigma for each mu. That's what you have. The mean field corresponds to the diagonal covariance, okay? That's where the mean field, to what the mean field refers to. So you have to find these parameters, like the mean of each one of the variables and the log variances. Again, we work with the log variances instead of the variances because we don't want to have any constraints in our optimization. Okay, that's why we use exp of omega, where omega is real, instead of sigma. Okay, So this is one class of one family that we could use. Another family that we could use is the full rank Gaussian, which is basically like this, right? So you have a mu here, and here you have a covariance matrix, but you don't work directly with the covariance matrix because it has to be positive definite, and this is a very hard constraint to enforce. So you work with a generalized Cholesky decomposition of the covariance matrix, where L is basically any lower triangular matrix with positive diagonal. And then the parameters you have to identify is this phi here, okay, which is mu and that L. So you have to optimize for these. Alright, so the variational problem now after the transformation, and now for this particular class of posteriors, looks like that. So you have to maximize the evidence lower bound. It is this expectation, okay? And here what you have is the entropy of Q. So you have to maximize the entropy of Q, which is good because the maximum entropy principle holds, and if you had nothing, you should just pick the distribution and maximize the entropy. And but it's not just the entropy, it is biased by this term, which has to do with your observations. Okay, and it has also the transformation that we did. Now, what I want you to notice is that this thing here does not depend on the data. The entropy does not depend on the data. This does depend on the data, and it involves an expectation over the posterior, the candidate posterior. It's an expectation over Q. Okay, and you want to minimize this thing. Alright. Now, this expectation here over Q, if you just wanted to evaluate this L of E, you can evaluate it by just sampling zetas from Q, plugging them in this expression and taking an average. So you could do a Monte Carlo estimate of this. Okay? Of this part. How do you do it? Sample zetas, plug them in there, 1 over n, sum of this quantity, you will get an estimate. Right? However, what you really want in order to maximize this is information about the derivative of L with respect to phi. But when you take the derivative of L with respect to phi, you have to differentiate also here. So the derivative doesn't just go inside the expectation. It's one of these unfortunate cases. So if you just put the derivative inside the expectation, you're going to get something that's basically garbage. Okay? So you need to worry about differentiating this guy. And to deal with that, we're going to introduce what is known as the reparametrization trick, which is also the state of the art in machine learning right now, but it is actually trivial. Okay, so the idea is to do one more transformation to make whatever we integrate over independent of phi. And I'll show you how it works. Alright, so the reparametrization trick, or otherwise known as elliptical standardization, works as follows. So our problem is here. Our problem is that we want to take derivatives with respect to phi, but we can't just put them inside the expectation. We're going to have to worry about that guy. So we want to remove zeta from the expectation, and here's how we do it. You know, it is specific on the class of distributions that you want to use to approximate the posterior. So if you use the mean field approximation, that's how you approximate the posterior. It's going to be a normal. So if you define a variable eta like this, so look at that. This is basically the square root of the covariance times zeta minus the mean. And zeta is distributed according to that. So you take zeta, you subtract the mean, and then you divide with the square root of the covariance. The result is going to be standardized. It's going to be a random variable that is standard normal. Okay, so that eta now is the standard normal. So if you apply this transformation, you get rid of that expectation over zeta that depends on phi, and the problem will become like that. So you change now, with that transformation, you change the expectation over standard normals, but you just have to add this transformation in there. It's not a big deal. Okay. Guess what? PyMC3 does that for you. Okay, so I'm just showing you what is inside the black box. All right, but the idea of the parameterization trick is this. All right, if you wanted to do it with a full rank approximation, then it's the same thing, but now the square root of the covariance is basically any matrix that satisfies that is basically the square root of the covariance, which is not uniquely defined, but this would work. Okay, if you just take whatever you have there as cell and you invert it and multiply it with zeta minus mu, then this will be normally distributed. Okay, so it can be done for this particular class of posteriors. And here's how it would look like. So you see our prior and our posterior, right? So you see what happens when we go through t and phi. Actually, we have already gone through t here. When we go through s of phi, which is the standardization, it basically takes the posterior and puts it around 0. It makes it a normal, basically. All right. So how do we solve the optimization problem? Now understand that this may be a little bit complicated, and this is totally okay. It requires a combination of at least 4 or 5 different concepts. Okay, so we used concepts. We had to know about Bayesian inference to get the posterior. Okay, you guys were familiar with that. We need to introduce the concept of information loss from information theory to define an optimization problem, the solution of which approximates the posterior. Then we had to use a few transformations to simplify this optimization problem. Okay. Namely, the first transformation was to take to remove any constraints from theta, so that they are just real numbers. The second transformation made sure that any expectation we may have does not depend on the parameters we're approximating, so we can just differentiate inside the expectation. Now we're going to solve. Now this is the fourth thing that we need. The fourth thing that we need is how to actually solve this optimization problem. So this uses elements from stochastic optimization. And because our problem is a problem of stochastic optimization, you have to maximize the expectation of something. All right, so this is the characteristic definition of a stochastic optimization problem. And now we can take derivatives with respect to phi, okay, because whatever we have here does not depend on phi, so the derivative operator will just go inside. And if you take the derivatives with respect to mu, you will get that. You can do that analytically, right? So there's no problem. The only problem is that you need this derivative. Okay? This derivative involves a derivative of your model with respect to the parameters. Okay? That's why PyMC3 and Stan use symbolic computation packages on the backbone as the backbone, so that they can compute this. So you just provide this, by the way. You don't even worry about any of that stuff. Okay. All right, so you have that. Everything else comes automatically. For the mean field, the derivative of L with respect to omega is this. Again, you can find it analytically. For the full rank approximation, it looks like that. This term right here comes from the entropy of a Gaussian, which is that h over there. You have that h. The entropy of the Gaussian does not depend on mu, so you have a 0 here, but it does depend on the variance. Okay? And that's why you get this term. But it is analytically known, the entropy of the Gaussian. Okay, so you have these gradients now. All right. And, but still, the gradients require an expectation. Yes?
How are the derivatives calculated with respect to the variable?
These derivatives?
Yeah.
Everything else, it's trivial, right? Because t is something that we have picked, etc. This thing right here is calculated automatically with automatic differentiation.
Does it form an approximation and then take the derivative of that?
No. it uses automatic differentiation, which is this is the sixth topic that I need to bring into the lecture to explain what is going on. So you write code for px theta, which is basically used by Stan or PyMC3 to create a computational graph of your model, and then on that computational graph it uses the chain rule to find the derivative of log px theta with respect to theta, not in an approximative way, but exactly. Okay, so it does the chain rule. The thing that you would do by hand happens automatically. That's why it's called automatic differentiation. Make sense?
Does it not require, what if your simulation model or computation model?
It doesn't work with that. If you have a finite element model, it doesn't know how to take the derivative of that, obviously. That's why we're not there yet. So there is if you have ANSYS, does ANSYS give you derivatives? Maybe it does. I don't know. Maybe you can make it spit out the derivatives. But let's say that it doesn't, okay? Then you're screwed. You can't do that. You can't do this thing. You're gonna have to approximate the ANSYS code, replace it with the surrogate, and then take the derivatives of that. That will be the approach forward. But if you have your own code, and let's say it's a MATLAB code, MATLAB can do automatic differentiation for you. It doesn't have, you can do it. Okay, you can it's just another package that you need to load. Now, if you have Python code, then there's absolutely no problem. Especially if it is not too long. Because you can change it into native TensorFlow code, and the derivatives are all automatic. Now, if you have a finite element problem that is solved in Phoenix, which is a modern finite element package for Python, Phoenix can give you the derivatives because you can do adjoint calculations and take the derivatives.
So the px theta is an analytical expression that we have.
Px theta, for this particular approach, has to be an analytical expression, okay? But it doesn't have to be one line. It can be several functions, okay, intertwined together, but they have to be implemented in native language for automatic differentiation to work. If you could take the derivative in any other way, then it will still work, okay? So for super complex models, I don't know, multi-physics simulators, you can't do this stuff yet. In principle, you could if you could get the derivatives, but getting the derivatives is not trivial. All right. So even though we have the derivatives here, to estimate the derivatives of L, we need to do expectations of the derivatives. And the only way we can do this expectation, one of the ways, is with Monte Carlo. So you can just sample etas, it's just standard normal, plug them in there, do 1/n, and approximate. And the question is, can you solve a stochastic optimization problem if you have noisy estimates of the derivatives? And the answer is yes, you can, if you're familiar with this algorithm, the so-called Robbins-Monroe algorithm. It's amazing that we're actually combining this, not us, these guys. We are just understanding what's going on. Many different concepts in order to achieve this. So here's Robbins-Monroe. Robbins-Monroe is an algorithm that allows you to solve problems of this form. So if you notice, this is the form of our problem, right? The expectation over some normal random variables, some random variables basically that do not depend on phi. And here we have to maximize the expectation of something, all right? So this is the kind of problem that we have. Only that f is a little bit longer, but that's what we have. Now, notice that the expectation doesn't depend on phi, and this is crucial. And we managed to do that. Now, Robbins-Monroe in 1951 showed that under very mild conditions for f, the following algorithm converges to the solution of the problem. And it's actually mind-blowing, okay, that it does converge, but let me show it to you. The algorithm says start from any phi you want and update it in this way. Add a little bit of a noisy estimation of the derivative, right? So you start at that phi of t. Actually, here at this point, I should have phi t. You start at that phi t, you sample etas, you plug them in there, you take the derivative, and you take the average, and you do that repeatedly, right? So you start at a random t, and you repeat like that. And this thing will converge to the maximum, but not for any a's. So if you here you put, I don't know, 0.0001, it will not converge. If you put 10 to the minus 6, it will not converge. These things here, this alpha t, which is known as the learning rate, has to satisfy a very specific property. And the property is this. The sequence of learning rates must diverge, but its square must converge, the sum of the learning rates. So this thing here, that the fact that the sum of the learning rates converges, tells you that the learning rate itself goes to 0. So as the algorithm progresses, the learning rate will go to 0. But this tells you that it doesn't go to 0 very fast. This is the difference. So there's a magic rate of convergence to 0 that A must satisfy in order to give you an algorithm that will converge to the maximum. Okay? And it's actually not very hard to prove that this thing will converge for some regularity assumptions on F. And you can go, the mathematicians, you can go and look at this paper. Now, this algorithm is basically the backbone of all modern machine learning developments. It's behind the successes of deep neural networks. This algorithm in particular. An algorithm described in the 50s. So that's why math is useful, right? So something described in the 50s allows you to do inverse image search right now. If that is useful. It also allows you to do other stuff. And it is this simple. This is the simple algorithm used pretty much all machine learning codes. But there's of course an issue. The algorithm guarantees convergence when the t goes to infinity, so at infinite steps. Okay, this is always the ridiculous thing we get in mathematical, with very powerful mathematical statements. So if you stop before infinity, you may get poor results. It always moves towards the maximum, but you are only guaranteed to reach the maximum when you wait forever. So there's been a lot of research on how to accelerate it. Okay, there is this algorithm, which I'm not even going to try to pronounce, that adjusts adaptively the learning rates in order to accelerate how it moves. But it works well in practice, but it doesn't. There's no theoretical guarantees that it converges, but in practice it works. And now these guys, Blake, Gelman, and all the other guys, they combined Robbins-Monroe with this algorithm. They modified this algorithm a little bit so that the Robbins-Monroe assumptions are satisfied. So they get an algorithm that adjusts the learning rate as it goes, but it's guaranteed to converge. And you can see the details in the paper. You should see the details in the paper, because we may use Sarmila. All right. So, and the algorithm now goes like that. The complete algorithm goes like that. Here's your input. This is your input. Your user input is this. Okay? You have to give the joint distribution of x and theta. Everything else will just happen automatically. Of course, at this stage, if you don't really know what's going on, we may still get garbage. Okay? It's not fully automatic. But it goes like that. It just iterates, uses this variant of the Robbins-Monroe algorithm to gradually maximize the evidence lower bound. Okay? and when it stops, it spits out parameters that estimate the posterior within the class you have specified, which for this particular case could be either the mean field or the full rank Gaussian. And it can also spit out an estimate of the evidence. So if you look at the value of the maximum evidence lower bound, that will be an estimate of your evidence. Alright, these packages implement automatic differentiation variation inference. Okay, so if you can define your problem in these packages, then you can just use it. Alright, and at this stage, at the current stage, those of you that do not have very complicated models, so if you have models that you can basically just write down perhaps in 10 or 20 lines of Python code, then you can just use that. Okay, it's more powerful than MCMC because it's almost in real time that you're gonna get the results. It's much faster. It scales better with higher dimensions. What else? So you can use it. If you are one of these people that have simulators that are external, black boxes that you cannot really play with, you can attempt to basically learn, I don't know, polynomial cow surrogates of them, for example, and then use this. Or you can look at the internals of PyMC3 or Stan, and I'm sure that it is doable, but you're gonna have to find derivatives of your code in one way or another. But there's no automatic way. You're gonna have to go to the GitHub page and look inside these to make it work. All right. For the rest of you, I mean, who is the rest? I don't know. I think I covered everybody. All right, so let me show you a few examples of how this thing works. This is a trivial example. This is an example I have in the paper where they say we just have one distribution that is basically just a Gaussian. I mean, they don't even have a theta. Actually, x is their theta. Okay, so their true distribution is this. They have a Gaussian centered at 0 with covariance, and they just want to approximate this with another Gaussian using variation inference, just to verify that what they're doing makes sense. Because if your posterior was a Gaussian, and you try to approximate with a Gaussian, and you don't find it, there's something seriously wrong with what you do. Okay? You see, this is the mean field approximation, which is, of course, cannot capture a Gaussian that is not isotropic. And then the full rank and the actual posterior match perfectly. Then they did a logistic regression problem. They did a lot of problems. These are just the validation problems. This is a logistic regression problem of the type we saw in our handout about the challenger problem, right? Logistic regression. I give you an X. Tell me if the label Y is 0 or 1. Has this failed or hasn't failed? So logistic regression had basically coefficients for each one of the features that you wanted to include. And if you do it in a Bayesian way, the way we did it, basically we used MCMC to characterize the posterior. So here you see a comparison of MCMC, which is the sampling, right? So the red, come on. So you see that the green curves correspond to a Monte Carlo estimate, a Markov chain Monte Carlo estimate of the posterior. This blue thing must be the full rank approximation, the posterior variational inference approximation of the posterior. And this thing right here should be the mean field. So you see that the mean field underestimates a little bit the uncertainty. Now, what you must note here is that the truth here is the sampling approximation. But the sampling approximation may require hundreds of thousands of evaluations of your model. The variation approximation may require hundreds of evaluations of your model. So the order of magnitude, the time required to obtain the results for variation inference are at least 1 order of magnitude less, right? So you need at least 10 times, at most 10 times. So you need, you divide the time by 10, okay? The complexity is much smaller, much lower. Another example that I want to show you, and one of the reasons I want to show you is because some of you do model identification, and this is a classic example of model identification, even though it's actually very simple. Model identification from time series. So this is a model identification example from finance, where you have the price of an asset like a stock. You assume a model for it. The model for the asset is that it is basically, its price is basically normally distributed with a variance that may depend on time, and that thing over here is called the volatility. Okay, the log of the variance is called the volatility. And you observe y of t, that's the price of your asset, or the log price of your asset, and you assume a model for the volatility, which here is just a linear model. So you assume that the volatility is basically some constant plus a term that depends on the previous volatility. So this is an autoregressive model with some initial conditions. These are classic conditions, assumptions that you would use in Kalman filters. And you want to characterize the posterior of all the hidden states of H and mu and phi. So you want to infer the hidden volatilities and the parameters of the model. So this whole thing here, this is just to illustrate how easy it is to do this kind of stuff. So this X here, the time series you do observe is your data, and then everything else, including the hidden states that you don't observe, which may be a lot, like 500 states are not observed in this example, and all the other parameters. This is what you would call theta. So everything, okay? And that's the likelihood, and that's what you have to program. So this thing here is just this, right? And this thing here is the autoregressive model, which is described here. It's very simple to implement. And then this is the result you get. This actually, you probably don't appreciate how difficult this problem is unless I give you a homework in which you have to do it with MCMC, and you see that it's completely impossible to do it in MCMC, to infer the hidden state with MCMC. The only technique that would work is ensemble Kalman filters. That's the only technique that would work. But you see here, and that's probably what they use here, but here what you see is basically the posterior mean of the volatility, okay, found in three different ways. The sampling approach, which I'm not sure exactly what they do, to tell the truth, but they definitely don't do standard metropolis because that would not work. They probably do a more a tailored variant of MCMC. Now the mean field approximation and the full rank approximation, which basically nails it. Now the sampling approach may actually take millions of samples to converge for this particular example. The variation approach can give you the results in basically a few hundreds of model evaluations.